Hello everyone, can everyone hear me? Yes, no? Okay. I'm Bryce, and this talk is called The Making of iOS 11 Jailbreak, Kiddie to Kernel Hacker in 14 Sleepless Nights. This is kind of my journey when I learned about iOS and the kernel. So let me tell you a little bit about myself, and then we'll jump right into it because we have a lot of stuff to cover. The name of this talk comes from Atlas's, The Making of Atlas, from Kiddie to Hacker in 5 Sleepless Nights. And he kind of inspired me when I was just a skitty, and I've been playing CTF ever since. You know, that was 13 years ago. I've been playing CTF for 13 years. I've been a DEF CON Open CTF organizer for the past 4, and I've been with Coalfire, the company, for the past 2. And as of a year ago, I used to be afraid of kernels. I came to Derbycon last year and took a class called Windows Kernel Primer by the Hungry Hackers. I'm sure people saw it last year. And it was amazing. It was a real eye-opener to go like, hey, this isn't magic. This isn't rocket science. This is just normal stuff, and you can get through it. So, what we're going to be talking about today is XNU. And this is the kernel that Apple uses for all their devices. So, the Macs, the iPhones, the iWatches, even the Touch Bar is running its own kernel. It has its own RAM. It does its own thing. So, Apple uses this everywhere, and it's kind of this duct-taped together bastardization of Open Software Foundation mock kernel and the FreeBSD 4.3 kernel. And so it's kind of like the combination. They took this microkernel. Mock is a microkernel. It's super small, barely does anything, but does it very efficiently. And then they kind of duct tape FreeBSD onto it to get all the functionality of FreeBSD. And it supports all those architectures listed up there. They dropped PowerPC because they don't make PowerPC machines anymore, which is fine. But the real kicker, and why kind of all this stuff came about, is that Apple open sourced the kernel, the XNU kernel, back in 2017. And this has always been closed source. Everyone has been like, you know, only the leadest of lead can get access to like the code, or they have to struggle through and reverse engineer it. And so a lot of open source security research has been performed, especially by Google Project Zero, and we'll talk about that in a minute. But that's kind of the impetus to this whole thing. So I do have a little bit of a warning. There is going to be a lot of C in here. But don't be afraid of the complexity that we're doing. We're taking simple abstractions. We'll call them Lego blocks, and we'll build like a building. All right? And complexity is our friend, because there are the bugs that we're using to exploit iOS are a result of this building complexity in the operating system. So just to say, the kernel is not black magic. It's not that complicated. And that's a little bit of a lie. It is complicated, but each individual piece is understandable and digestible. You know, it's going from arrays of just like a sequence of things in memory, to structs, sequence of things in memory with types associated with them, to linked lists, which are just structs that have a pointer to another struct. And then upon those kind of basic dumb computer science models, we can build all of the abstractions that the kernel uses. And I'm sure everyone here is familiar with like how heaps work. You kind of ask for memory, it gives it to you, you hand it back, it takes care of it. It's all garbage collected, it's not under kind of your jurisdiction. And so that's what the power of like using these building blocks gives you. Now there's a couple of abstractions that are XNU specific, so tasks and mock ports are the two that are just slightly different than other operating systems. So a task in XNU is very analogous to the eProcess structure inside of Windows. It's a collection of everything that the kernel needs to know about a program to run it. So like the state, where it lies, what permissions it has, where its memory is mapped, is it memory mapped, or is it paged down. So it's just a collection of data surrounding a process, and it's all built out in a nice little struct that we'll see later. And then the next thing, which is different from a lot of other operating systems, is ports. Mock ports are a derivative of a real-time operating system's kind of IPC. And this is what Apple heavily relies on when they duct tape BSD and XNU together. So mock ports are just like mailboxes. You say, hey, I have a mailbox, then that makes you responsible for receiving messages coming out of it. And then you can give your address to someone else and they can send you messages. And you can give your address just once, or you can give it permanently. So just think of a port as a mailbox. And so as we move further and we build up complexity, it's just a mailbox. It's just a way of talking to the kernel. And so when we look at the entire kernel, there's a lot to it, but we only care about the user space, because we're living in user space. We're trying to jump into the kernel. How we get and how we talk to the kernel with the IPC mechanisms, such as mock ports, which we're going to dive deeply into, and then the kernel task. Everything else doesn't really matter for what we're looking at. We don't need the extra complexity. We're not doing baseband exploitation. So what we're really excited about is how we can talk from a user space task down to the kernel task. All right? And so why do we even want to jailbreak iOS? Well, there's a couple of reasons. Like, I like having full control over my device. I like the ability to have root on all my boxes. I do, as part of my job, I do mobile app testing. I need jailbroken iPhones to do this because, as you know, if you try and download an app from the App Store, it's encrypted per device. And so there's a plethora of reasons, but if we move forward and we say, all right, what are our prerequisites? We need to have some way of interacting with the system, so either SSH or web, what have you. We need root, and there are multiple definitions of root, as we'll see coming up here soon. And then we need to be able to run our own code. Because we want to build our own tools, we want to do security research, we want to break things, right? And so what we need is an exploit. Exploits cost money, but that's why there hasn't been a lot of jailbreaking since 10, or before 10. There was a big kind of lapse between 8.4 and 10. And these exploits are worth a lot of money, so a lot of people haven't been doing work on them. However, when Apple decided to decrypt its kernel caches, all of a sudden, this is like their prerequisite to open sourcing the kernel. All of a sudden, everyone can see the kernel cache and do reverse engineering on it. Google went, okay, let's put Project Zero on this, and they set up a bunch of research people and started looking for bugs in this, and then they decided to release them openly. And so that's why we have kind of the bugs used to break iOS. So this guy, Ian Beer from Google Project Zero, tweeted in early December, hey guys, keep your devices locked on 11.1.2. Now, as kind of context, nobody had released an exploit for 11. Like, this is new territory. There's a lot of changes from 10, and it was kind of a big deal at the time. And then he followed through on his promise a couple days later, and he released an exploit getting task for PID 0. So, what is task for PID 0? In XNU, root does not equal root. So, say in the Linux kernel, or in Windows, if you're a system, you can talk to kernel processes. You can't in XNU, because there is layers of protections against it. Apple kind of designed a lot of things away from the user and to try and create this sandbox environment for their applications. So what task for PID does, if you all are familiar with like ptrace on Linux, task for PID gives you introspection into another process. And so when we say task for PID 0, we want to talk about that kernel task shown previously in that graph. So that lets us look into the kernel structures and see what's going on and play with those structures. And you can do anything, like you can do crazy things with these mock VM star calls. You can write, you can create threads, you can create memory spaces, you can remap, you can change all this stuff. But Apple, knowing that, yeah, of course, jailbreakers are going to use this, decided to say, all right, you try and get a task port for the kernel? No, we're not going to give it to you, which kind of sucks. But the reason that task for PID, in the context of jailbreaking, is better than kernel code execution is because of the hardware built-in protections on the device. Okay? So in ARM, which all your iPhones are running, you're either running 32-bit or 64-bit, you have 4 execution modes, which are analogous to like x86, rings privilege, right? So everything in user land runs in ring 0. The kernel code runs in exception level 1. They don't really use exception level 2. Well, that's built for hypervisors. I haven't really seen people use EL2, but it'd be interesting to see. And then they have this process in EL3 called Watchtower, right? And this is your kernel cache protection. It goes through memory, and it hashes every single page of memory inside of EL1, the kernel space, and then compares it to see if it's been modified. If it is, it borks the kernel, everything goes down. So, that's why we want task for PID 0. We don't necessarily want kernel code execution. So when Ian Beer released these set of bugs, he labeled them Async Wake because they were part of the IOKit derivative library. And there were two bugs that he released, an information leak in the kernel, and then a use after free. And then he kind of nicely wrapped them up into an exploit chain for us. The information leak is needed because the kernel, upon boot, has 9 bits of random entropy in where it's loaded into memory. On Linux, I think this is 12. On Windows, I'm guessing at 14. But so it's kernel address space randomization. You can't rely on rock gadgets. You can't rely on other data structures being present if you don't have an information leak. And so, hopefully, oh no, I can't read that. Okay, I will talk through it. The information leak he discovered is part of a function called procinfo. Now, procinfo just gives you your process info, or if you're root, it gives you other processes info. He found a bug in where you can supply the list of pointers, and it'll tell you if those pointers are inside of the space. Okay? So inside of this function, they do this division down with integer division, and then they repopulate it, and then all of a sudden, if you can bypass Apple's protections down by the bottom, it'll copy out your buffer to user mode. And I guess the exploit is the easiest way of seeing this. Here's the information getting leaked out right here, stat plus 7. So when you request this information and you don't give it a full pointer size, which in 64-bit is a Q word, so 8 bytes, you give it 8 bytes plus 7. All of a sudden, it'll give you the extra 7 bytes, and then you have a 7-byte information leak. Now, he wrapped it up in a function and then ran it over the top 100 processes, I think like 1,000 times, and did some statistical analysis to determine, okay, what's the most popular kernel pointer that's coming back? Because you can see all kernel pointers begin with that 00, and then 8. And then after that, you can derive the kernel slide, where the kernel lies in memory. Okay, bug number 1. Bug number 2 is kind of a systemic bug due to the mock interface generator. Now, there's kind of a history behind this. Apple goes and creates all these extra layers upon layers and layers. They don't really have the single point of history that, say, like the Linux kernel has, where like 1 or 2 people know from the very beginning what every single thing does. So it's kind of like institutional knowledge. So they have these MIG generators that it's a bunch of C code that writes more C code. So, yes, there are bugs here. There are a ton of bugs here. And this specific bug lies in the IO Surface user client. And Ian Beer talked about this in his that brief history of mitigation, the path to EL1 and iOS 11. And it's a combination of, there are predefined requirements for this MIG interface. If you say, hey, I am going to run a function and it returns an error, you're responsible for cleaning up the memory. If it doesn't return an error, the kernel takes care of it. And so the bug here is that IO Surface user client doesn't properly clean up its memory after it receives an error. So the exploit code for this is just to run it 3 times, it'll bork, and then you have a floating task port in memory, in kernel memory. So, it's pretty cool. It's a pretty interesting bug. How are we doing on time? Okay, good. So, this is kind of the exploit food that he's come out of this. I don't necessarily think we need to deep dive into this because as jailbreakers, we're looking at this as like, oh, this is a Lego block I can build on. I can build on this primitive that gives me this task for PID 0. But as you can see, he does a lot of heap feng shui. He builds out a fake kernel task port and sprays that across memory using his use after free, and then all of a sudden we have a task for PID 0, which is Now, all right, we can access the kernel. Yay! So I ran the exploit, and it was super exciting. Absolutely blank screen. But if you look at the Xcode and the console debug output, you'll see it starts to, it has some information, and then all these numbers start to increment down, and then you hit 199, and then some more information, and then all of a sudden, boom, we have this ability to talk to the kernel pointer. We are able to have a task port to talk to the kernel. Yay! All right. So now with this in mind, let's go ahead and jailbreak the system, okay? So, this terrible graph was maybe 12 days in or 11 days in when I got really, really desperate, and I couldn't figure out how to do one of the things. And so I'll go into that later. But we have a couple things that we have to do to hit our original prerequisites, right? We want to get root. We have to bypass as many sandbox limitations as feasible. We have to turn the hard drive on as read-write, so we have full control over that, because normally it comes just read-only. And that's Apple's way of protecting it against just rogue apps that somehow break out. Then there is this idea called platformization, right? Platformization is a flag in memory saying, hey, I'm an Apple binary, I can do what I want. And that really helps us accomplish our goals in getting full control over the system. And then adding entitlements. Entitlements are a series of permissions that are defined and signed by Apple. And as we go through later and we see all the signing stuff, everything Apple gives out has a privilege. So as you as a developer, you get certain privileges. Apple gets certain privileges. Enterprises get certain privileges. And you can't go above that. I want to give myself the ability to get crazy entitlements, but I can't because my certificate chain shows that I am not entitled to do this. So we need to bypass that. So let's start at the beginning and break it down, because it looks really complicated. We'll break it down. So getting root is super analogous to token stealing on Windows. Windows, you iterate through the processes and you grab the credentials out of the eProcess struct in process 4, which is system. We do the same thing. We just look for the kernel task, and then we copy their credential pointer. We're root. So you think, okay, this is kind of gobbledygook. Let's look at Apple's sources. Apple's released their sources, and inside of the process headers for how they store processes in the kernel, you can see, all right, we have a struct proc, we have a linked list at the top, and then we have our process ID. Okay, this is pretty easy to follow. We have our user permissions, our UID, our GID, and our UID, and then down at the bottom we got our credential structure. So it's as simple as setting our permissions to 0, the root user, and then we just copy the credential pointer out of the kernel task process, and we copy it into ours. And this is kind of analogous with these two lines right here. And these are kind of just for posterity and later for further inspection. So that's all we needed to do to get root. But like I said previously, root on XNU is not root. So there's other sandbox limitations that we have to start bypassing. So in creation of pages of memory, there are certain restrictions applied that Apple uses as a competitive advantage. Okay? So the ability to create a read, write, and execute heap page is very important to high-performance things. So think Chrome, think Firefox, think Safari. They have JIT engines that turn JavaScript into native assembly and run that. This is how Apple keeps their competitive advantage in their browsers. They don't allow anyone else, except for Safari, to have read, write, execute pages, so that everyone else's browser runs slowly. Don't ask me why. So, as I mentioned previously, the root directory is mounted as read-only. Binaries can only be run in certain directories. You are not allowed to run anything out of temp. There's several policies in place on the system that look as you perform an execv, and if they say, oh, no, you're coming from a bad place, I'm not going to let you run. Okay. Our entitlements are bad. We're not a platform binary. And as of right now, you need a developer certificate to properly sign code to run on the device. But we don't want that. We want to run anything. So let's go ahead and remount the drive. And it's as simple as this. But it's almost as simple as that. What we're doing is we're just doing a mount update of type Apple file system to the root drive, and we're going. Now, the reason that this didn't work initially, and I was ripping my hair out going like, what, this should work, was because of these flags. So when the root file system is identified upon boot, these flags are applied to it in its vnode structure. And we'll get into that in a minute. But it's defined as read-only, and then as it's a root file system. So those flags put together when it's first mounted say, nope, this can never be read-write, this is read-only. So I ran around online and I found somebody who had an idea. Let's swap those flags out, let's remount it, and then we go. So it's actually pretty easy. It's pretty easy. We looked at the kernel structures, and there is a master vnode. And the vnode is just a type, it's a data type. I just think of it that way. It's an easy way of saying, here I have a file, I have drive, what have you. So we look at the master vnode inside of the kernel, and then we look in the structure. And I do apologize for the tiny text, but there is mount at the very bottom. And where that mount points to, we have a flag. So great. Now we know, all right, if we change the structure, all of a sudden, and then we remount it, we'll get root. Or we'll get a read-write file system. And that's essentially what we do. The code above does parsing into the kernel, and if you look at the jailbreak I've put on GitHub, this is why it only works for a certain type of kernel, is because I've hard-coded the root vnode address. But that aside, all we are doing is we're parsing into that structure, we're flipping those bits. I'm not sure the right term for this, but the inverse of 1 is E, and the inverse of 4 is B. So just think of those bits being set. So we just and that, so we turn them off, we remount the drive, and then we quickly put them back. So, easy enough. All of a sudden, the root drive is now read-write, and we can do whatever we want with the file system, which is dangerous, which is why you should be careful about package installers. They might actually fork your device. That's another story. So platformization. What do we need platformization for? Well, it gives us the ability to talk to other processes is the main thing that we care about. There's a couple other attributes to it, but we need to say, hey, I need to talk to task for PID for whatever PID I want. Okay? And again, it's our simple, it's our friendly proc structure that we've already seen, and it has a task pointer. We look in the task pointer, we look down, and there are our flags. And there you go. That's all you have to do. There's the C pseudocode up top and then the actual C code below. All we have to do is OR our flags with 400, and then we're good to go. And this is all live. This is all live. We don't have to refresh anything. We don't have to do anything. We just say, make it so, and then any further call in the kernel, it checks that value, and we're good to go. So, at this point, I think I was like 11 days deep and going like, oh my gosh, I don't know how to do entitlements. Entitlements are a little more complicated. And so I ended up reversing Chillin, which is a jailbreak by Jonathan Levin, and he clopen sourced it. He gave out the object files and a header, and was nice enough not to strip the object file. So reverse engineering was fairly easy. But there is the here be dragons part on the bottom right-hand side, where I was like, I don't really know what to do here. But using his code as kind of a reference, I went through, I said, okay, why, or like how, in the process of building out how we get our entitlements, here are the reasons why we need them, okay? So, going back to the whole, root on XNU is not really root. There are several things that make you not root when you're root. And one of the things is AMFI. AMFI is the Apple Mobile File Integrity Daemon. And it's always running on the system, but we'll get into that later. Without an entitlement for task for PID, even though we're platformized, it doesn't work, because the system checks our entitlements and our flag that we previously set. So Apple, in their wisdom, uses XML for everything. You want some bugs? They do XML interpretation in the kernel. Go look at that. So the entitlements that we need are specifically, I should have put them in order, but we need task for PID allow. We want kernel system override, we want unsigned code, we want to do all the things on the system. But we don't have that, and we can't have that because we don't have an Apple certificate. We only have a developer certificate at this point. So, it's just like before. We have a couple structures to process through, and starting with the proc structure, which we've done previously, we jump into our vnode, because processes are vnodes as well. It's just an object. And then inside of the vnode, there is an internal code signing section. And this code signing section, Apple uses as part of their X509 chain of certificates to build out who are you, what sort of entitlements you have, what sort of code can you run. But it's actually pretty easy to modify. All you have to do is look at the size, because you need to keep that in mind when we rewrite the blob in memory. And then we just need a pointer to our entitlements blob, and then we need a pointer to where it stores the hash. So what our plan of attack is, we're going to put our new entitlements in. We're gonna SHA-256 them up, and then we're gonna write our hash to where it expects it, and then we need to overwrite the old entitlements blob with our new one. So it's simple. We're just replacing them, right? So the code for that is more involved, and I won't get into that. But the idea is conceptually there. All we have to do is just replace our entitlements and move on. So they're looking at the full sandbox limitations, though, there are some things that we can't touch. We can't create read, write, execute pages. We have turned the root directory and read, write, but there are some policies still in place where we can't run binaries. There's not much we can do about that, except for create binaries on the root of the file system. We've platformized ourselves, we fixed our entitlements, and now our last hurdle to get over is running unsigned code. So, running unsigned code is not possible, kind of. So this amphi daemon will check every single executable, and if it doesn't properly have the signatures in place, and then the certificate chain in another section of the binary, it just kills it. It's like, nope, you're not on the system. But, I mean, we are root-ish. We are a platform binary. We now have Apple privileges, and we have these super awesome entitlements. We are entitled to do pretty much anything on the system. So, I looked at kind of the code flow when you create a process, right? So when you create a process using, say, like POSIX spawn, because this is touching the FreeBSD part of the kernel, you call execde or whatever in your C, and then it pops up the kernel, goes like, hey, I have a request for a task. All right, bring it over to Amphi. Amphi, you should check it, and then it brings it back down to userland. Amphi daemon is running in userland. It does the checking in userland. This does not make any sense, but hey, it works. So let's attack the user space process. I don't know why they don't do code signing in the kernel, but all right. So there's two ways of doing this. One, Amphi has a cache of known hashes of files that it's already verified, so it doesn't have to do the work. So you have a commonly run process, the hash is already there. Or we can patch it and create a custom error handler to catch any errors when it dies, and then we put in a bug. So it crashes every single time it tries to run a binary. And so this is what I went with. So Amphi is like a tiny binary. All it has is just some function pointers, some callouts. Like that is like an accurate representation of how big that file is. It is pretty tiny. So you can pop it up and like I use Binary Ninja. I popped that up and then there, and then I looked at the address, the offset to this MIS validate signature function. That gets called when the kernel wants, hey, check this binary, see if it's valid. So what we're going to do is we're going to put in a non-canonical 64-bit address. That thing is going to crash every single time. So then we set up an exception handler. And like I said previously with mock ports, they're just mailboxes, right? We tell the kernel, hey, anytime this process dies, send me a message. Send me its register state, send me its memory, send me its stack, anything else that's going on with the system. And so that's what that is. We can create a separate process to deal with this, and it'll handle all of Amphi's deaths as we kill it repeatedly. So once we've triggered a fault inside of Amphi by running a program, now we need to actually handle it and return the value true. Because all the kernel text is looking for is, hey, userland amphi, is this process signed? Oh, great, it is. Let's run it. So all we have to do is set up some registers with the new hash, and then we take, we write a 1, as in like true, into x20, and then we set up the old state, which is, if you're familiar with x86, the link register is essentially your first thing on your stack. That's a bad analogy, but it'll work. And then we just say, hey, all right, everything's good, keep running, go. So, I have a live demo. See if it works. One funny thing is I'm using QuickTime to do this. QuickTime apparently just plugs into your phone. Looks good. I'll pull up Xcode where the project is, and you'll be able to see the output, and we'll follow along as the jailbreak is run. So that's the right phone. All right, we're gonna run. Takes a couple seconds because it has to do code signing on my machine to get the app off the phone. And from there, I'll go ahead and clear the history. I'll hit run. All right, and so what's happening right now is it's using Ian Beer's task for PID, async wake, or his async wake to get us a task for PID. And here we go. We have the task for PID for the kernel. Okay. Then we go through and we attempt to obtain root. We see our current privileges are 501, which is mobile user. Okay. So we're in user mode. And then we go ahead and we very nice. We go ahead and rewrite our cred structure and then our UID, and RUID, and then all of a sudden, bam, we're root. Okay, great. Then we set ourselves our platform attributes. We go ahead and remount the drive, and then here's the entitlement section. I threw a bunch of crap entitlements here for things I really don't need, like accessory wireless configuration, reader session format, because it needs to be big enough to hold the new entitlements. So I take those entitlements, that's the old hash, and then I replace them with the new awesome, amazing entitlement. And then I rewrite the hash, call it a day, we're now entitled. And then the rest of it is just writing files to the system and setting up the amphi process to deal with amphi's errors. So now at this point, this is in my history. Yeah. So the thing worked. It does not. Great. So my IP address changed on my phone. Any fact parts enough shipping to be done on the next. Alright. That handout. Alright, so should be able to connect. Alright, I'm in the system. I'm root. And there's all of, yeah, we're root on the box. So, from there, I built in a web server to do, first of all, I wanted to pull files off the drive because I was worried about losing my phone. But then I built a kind of live kernel introspection setup. And so here's our kernel task with PID0. Here's where we're at. Down here, we're running a drop air web server. And we can look, and we can match up one-to-one with the source code going on here. And hopefully this isn't too small. And I apologize for this. But you can see like, oh, here's a link pointer backwards. Here's a link pointer forwards. Here's our PID. And here's all the relevant information, right? So it matches up one-to-one, well, almost one-to-one with their source code. So it's actually not too hard to follow. And I was really surprised by this because I thought previously, like, this is black magic. This used to be relegated to the gods of hackery. Like, no, anybody can do this because I can match up structs to anything. So, all right, let me pop back in the presenter mode. So kind of lessons learned, looking back at what was done. Don't do this. I know that's kind of rough, but the Chillin, which is a project by Jonathan Levin, and then Electra, which is a project by Coolstar, both provide great solutions with a lot more support than my jailbreak has. And they also have larger support communities around it, whereas I'm just one guy, and I did it for fun. And there's a lot to be said for having a community of people like helping you out and assisting and encouraging, because if you attack a hard problem by yourself, you get overwhelmed, and then you have to do what I did and just break it down into small chunks. And there's always this disparity between the XNU kernel sources, because they only give you the x86 sources. They don't give you the ARM sources. And so there is a little bit of like not one-to-oneness as you're looking at the code. You might see, oh, like this struct doesn't really line up, but I see this here in memory. There's that kind of problem. But having that community who's already solved those problems will really help. So please get involved. Like I'm a newcomer to the jailbreaking scene, like the first time I've done it. And there's been a lot of cool and really awesome people, especially on IRC. But one thing I have noticed is don't ask for when the next jailbreak is coming out, because you'll just get auto-banned from everything. Because people hate that. Because exploits cost a ton of money, and you know, no one gives them away for free. So, all right, where do we go from here? iOS 12 is currently out. Alibaba produced a video saying that they are showing that they had a jailbroken device. Also, Luca Tedesca, I forget his Twitter handle, but Luca has produced a jailbreak as well. But these are all private; these are not public. So at this point, we're either hoping that someone releases their jailbreak or releases the exploits, and then we can plug them into mine or Chillin or Electra. You know, with that plug and play ability of Task for PID, you can just get a new exploit, plug it in, and let it go. There are some new hardware security mechanisms that are intrinsic to iOS 12, especially that are all only enabled on the newer phones. The newer phones have a different type of chip that does like pointer tagging and a couple other hardware very specific things. So, yeah, I need to get my hands on one of those devices, and we can keep looking at that. So, go find some bugs. Does anybody have any questions? I think I'm like 3 or 4 minutes early. So, yeah, go for it. Oh, perfect. Whoa.
Nothing. Yeah, here it is.
Sweet.
So when you decided that you wanted to just overwrite those pointers in, I have to go back a couple slides. Why didn't you just tell the check to just ignore like everything in temp, like just change it to something else, some other directory, so then you could just copy data into temp and then run it from there?
So that is a viable solution, and I have to validate what I'm about to say, but I believe KTRR, the kernel, so there's KPP, which is kernel patch protection all over executable segments. KTRR looks at the read-only segments, and I believe those permissions, which are part of CPO, are inside of the read-only section. So if you change those, Watchtower is going to catch you. So I think that's why all the jumping around had to be done. But I will double check on that, yeah. Anybody, I'm up here. Let's do this. Yeah, probably. All right, and I think, unless anybody else has any other questions, we'll finish a little early. All right, thanks everybody for coming out.